Hey everyone, and welcome to another deep dive.
Yeah, welcome back.
Today we're going to be talking about electricity and electronics.
The fundamentals, right?
Yeah, the fundamentals. Um, and we are going to be looking at Chapter 12 of an aviation technical manual for this one.
And that's going to be fun because we're going to get to talk about, all the little shocking bits of how electricity works.
You have the invisible forces, the shocking
Oh,
surprises,
spectrum.
all that good stuff. Um, so to kick things off, let's start with the most basic element, matter itself.
Right. So to even understand electricity, you got to go back to the basics.
Yeah, the basics.
And the manual defines matter as, anything that takes up space, anything that has mass.
So basically everything around us.
Everything. Yeah. Everything you can see, everything you can touch, that's matter.
Okay, so we've got matter. But what makes up matter?
Right. So, you got to go one level deeper.
Yeah.
And matter is made up of elements. And you can think of these as like the building blocks of the universe, like the Lego bricks.
Oh, I like that analogy.
Yeah, so all these different elements.
Yeah, what are some examples of those Lego bricks?
Sure. So I mean, you're breathing one right now. Oxygen.
Okay, so oxygen.
And then another one is hydrogen, right? It's the lightest element.
Okay.
And these elements, just like Lego bricks, can be put together to form compounds.
Yeah, so like water,
Water, yeah.
H2O, 2 hydrogen atoms, and 1 oxygen atom.
Right, and figure 12 in the manual shows that. Like, it shows 2 hydrogen atoms and an oxygen atom all put together. And it's incredible how these tiny building blocks, create something as essential to life as water.
Yeah, it's amazing. So we have matter, which is made up of elements, which then combine to form compounds. But to understand electricity, we need to zoom in even further.
Right, we got to get down to the atomic level, like go down.
Down to the atom.
Down to the atom. Yeah, so if you zoom into an atom, you'll see that at the center of every atom is a nucleus. And this nucleus contains these particles called protons. Protons have a positive charge. And then there's also these particles called neutrons, which have no charge.
And then whizzing around this nucleus.
Right, you have these tiny little electrons.
With a negative charge, right?
Right, with a negative charge whizzing all around.
Yeah.
And it's the behavior of these electrons, particularly those in the outermost shell of the atom, that determine an element's electrical properties.
Okay, so these electrons, particularly the outer ones, are really the key players when we're talking about electricity.
Right, they are the key players.
So can you tell us a little bit more about how electrons influence conductivity?
Sure, so imagine this. Some elements, like gold, copper, silver, these guys have a bunch of free electrons in their outer orbits, in their outer shells.
Oh, so they're free to move around.
Freedom around, yeah. Like little nomads just, drifting from one atom to the next. They're not
Yeah.
tied down to one specific atom. And this easy movement, this free-flowing movement of electrons.
Makes them good conductors.
Yeah, makes them excellent conductors.
Rip.
And figure 12.3 actually shows just how many free electrons copper has, which is why it's so commonly used in electrical wiring.
Oh, that makes sense. So copper is a good conductor because those electrons can move so freely. Now, what about insulators? What makes them different from conductors?
So insulators, think about glass or ceramic or plastic, right?
Yeah.
These materials are the opposite of conductors. They're electrons, they're like homebodies.
Oh, so they're stuck in place.
They're stuck, yeah. They're tightly bound to their atoms and not free to roam around.
Okay.
And figure 12.4 actually shows this, like the electrons just kind of staying put in these materials.
Right. So in conductors, the electrons flow freely, and in insulators, they stay tightly bound.
Mm-hmm.
But what happens when those electrons start to get a little bit more rebellious, I guess you could say? Let's talk about static electricity.
Ah, static electricity. Yeah, static electricity. It's all about the imbalance of charges on a surface.
Okay.
So think about rubbing a balloon on your hair.
That's a class.
The classic, right. So that friction causes a transfer of electrons, creating that static charge.
And then when you touch something or someone, zap, you get that static shock.
Exactly.
Besides being a little bit annoying, can static electricity actually cause any serious problems?
Oh, yeah, it absolutely can, especially when it comes to sensitive electronic components.
Okay.
Like they can be really delicate.
Yeah.
And the manual actually shows in figure 12.13 how that static discharge, they call it ESD,
ESD, yeah.
can really harm those delicate little circuits in our electronics.
So it's not just about avoiding that little zap, it's about protecting our gadgets.
Exactly.
Our manual also mentions that the charge concentration is greatest at the sharpest points on an object.
Right, right. And that's why lightning rods, for example,
They're pointed.
they're pointed, yeah.
Figure 12.13 shows that, like how it's unevenly distributed.
Yeah, it's almost like those charges, they're just crowding around that sharpest point, just waiting to jump off.
Like they're looking for an escape route.
Exactly. And that kind of brings us to another force that's closely linked to electricity, which is magnetism.
Magnetism. Yeah, the invisible force that makes magnets stick to your fridge.
And makes compasses point north.
Yeah, exactly. But what exactly is magnetism?
Right. So magnetism is basically the ability to attract certain materials, particularly things that have iron in them.
Okay.
And every magnet, has two poles, a north pole and a south pole.
Right, so kind of like how electricity has positive and negative.
Exactly. Very similar. And just like with electric charges, these poles exert forces on each other.
So opposites attract and like poles repel.
But exact.
And surrounding every magnet is this invisible magnetic field.
Right. This invisible field.
And figure 12.14 in the manual actually shows that. It shows how one end of like a magnetized strip, it always points towards the Earth's magnetic pole.
Yeah, like a compass.
Yeah, just like a compass.
Yeah.
And figures 12.15 and 12.1, they also show these lines of force.
Yeah, those magnetic field lines.
And you can see how they interact, right?
Yeah, how they repel or attract each other.
Okay, so we have these invisible forces, these magnetic fields, but here's a question. What happens if you break a magnet in half? Does it lose its magnetism?
Ah, good question. And the answer is no. It actually creates two new magnets.
Oh, wow.
Each with their own north and south pole. Figure 12.22 actually shows that...
So the magnetism just, like, keeps going.
Yeah, it's like it never ends.
That's pretty mind-blowing.
But here's where things get really interesting. There's this, like, intimate connection between magnetism and electricity.
Okay, here we go. Now we're talking.
Right. We call it electromagnetism. And the manual talks about how Hans Christian Ørsted made this groundbreaking discovery.
What did he discover?
So he was doing an experiment, and he noticed that when he had a compass needle near a wire that had current flowing through it, the compass needle started going haywire.
Oh, wow. So the current in the wire was affecting the magnetic compass.
Exactly. It showed that moving electric charges actually create a magnetic field.
That's pretty amazing.
Yeah, pretty groundbreaking.
So figures 12.26 and 12.27, they showed this, like how the magnetic field around a wire that has current flowing through it, it's these concentric circles.
Yeah, those circles around the wire.
Right.
And to figure out which way that magnetic field is going, you can use something called the left-hand rule.
The left-hand rule, what's that?
It's a handy way to, like, visualize it. Figure 12.29 in the manual shows how to do it.
Okay, I'll have to check that out.
Yeah, it's pretty cool.
Okay, so we've talked about matter, atoms, electrons, static electricity, and now this link between magnetism and electricity.
Yeah, we've covered a lot of ground.
But now we're ready to dive into, like, the nuts and bolts of electrical circuits.
Yeah.
Let's talk about current, voltage, and resistance.
Yeah, those are the big three, the key ingredients,
The G players.
the key players.
Yeah. So let's start with current. What exactly is electric current?
So current is basically just the flow of electric charges. You can imagine it as like a stream of electrons moving through a wire.
Okay, like a flow of electrons.
Yeah, a flow. And we measure current in amps or amperes.
Okay.
Now, to understand what drives this flow of current, we have to think about something called potential difference,
Potential difference.
which is also known as voltage.
Okay, voltage. I've definitely heard that before.
Right. So imagine two tanks filled with water, and they're connected by a pipe. The difference in the water level between those two tanks.
That's the potential difference.
That's the potential difference,
Yeah.
yeah. The manual shows this in figure 12.37.
Okay.
And that difference in water level, it's like the pressure that's pushing the water from the higher tank to the lower tank.
Oh, okay. So in electrical terms, the voltage is kind of like the push behind the current.
Exactly, the push. Voltage is what's driving those electrons from a point of higher potential to a point of lower potential.
Got it. So we have the push, which is the voltage, but there's also something that's kind of pushing back, right?
Right, there's something resisting that flow, and that's resistance.
Resistance.
Think of it like the friction in a pipe. It slows down the flow of water, right?
Yeah.
Resistance opposes the flow of current, and it's measured in ohms.
Okay, so the push is voltage, the flow is current, and the friction is resistance.
Exactly.
I like those analogies.
Yeah.
But what factors actually affect the resistance in a material? Like, why are some things more resistant than others?
Well, The material itself plays a big role. Some materials are naturally better conductors than others, meaning they have lower resistance.
Okay.
The manual actually has this cool resistivity table in figure 12.42 showing how different materials stack up.
So copper has a low resistivity, which is why it's so good for wiring.
Exactly. Then there's the length of the conductor. The longer the conductor, the more resistance it offers. Think about a garden hose.
Oh, yeah. A longer hose is harder to push water through.
Right, more resistance. And then the thickness of the conductor also matters. A thicker conductor will have lower resistance.
So it's like a wider pipe allows more water to flow through. Okay, so material, length, thickness, those all make sense. Are there any other factors that affect resistance?
Yeah, one more important one is temperature. Generally speaking, as the temperature goes up, the resistance goes up too.
Oh, interesting. So things get more resistant when they heat up.
Yep, you got it.
So we've got the push voltage, the flow current, and the restriction resistance. But now let's talk about the power of electricity. What exactly is electric power?
So electric power is the rate at which electrical energy is being used or converted.
Okay.
We measure it in watts, like when you see a 100-watt light bulb.
Right, so that tells you how much energy it's using.
Exactly.
Okay, and how do we calculate power?
The formula is pretty straightforward.
Yeah.
Power, P, equals voltage, E, multiplied by current, I. So P equals E times I.
Okay, I'm starting to see how all these pieces fit together. Voltage, current, resistance, and power.
They're all interconnected.
Yeah, it's all coming together. But before we jump into circuits, you mentioned something interesting earlier about magnets.
Oh, yeah. There are actually different types of magnets.
Really? Like what?
Well, there are natural magnets called lodestones. And then there are artificial magnets, which are man-made.
Okay.
And then there's electromagnets, which are created using electricity.
Oh, that's cool. Figure 12.34 in the manual shows these different types.
It's pretty fascinating. From naturally occurring magnets to those we create with electricity, the world of magnetism is full of surprises.
Absolutely. But now let's get back to circuits. What are circuits and why are they so important in the world of electricity?
So circuits are basically the pathways that electricity follows. Think of them like the roads and highways for electrical current.
Okay, so the wires are like the roads and the electricity is like the traffic flowing through them.
Exactly. And our manual focuses on two basic types of circuits: series circuits and parallel circuits.
Okay, so what's the difference between a series circuit and a parallel circuit?
Well, a series circuit is like a single lane road. All the components are connected in a single line, one after the other.
So if one part of the circuit breaks, the whole thing stops working.
Yep, that's the downside of a series circuit. If one light bulb burns out, the whole string goes dark.
Oh yeah, I've definitely experienced that with Christmas lights.
Right. But they do have some advantages. In a series circuit, the current is the same throughout the whole pathway, which makes it easy to control.
So if you want to control the current in a series circuit, you just have to control it at one point.
Right.
Okay, now what about those parallel circuits? How are they different?
Think of a parallel circuit like a multi-lane highway. The components are connected on different branches, so there are multiple paths for the current to flow.
Oh, so if there's a blockage on one branch, the other branches can still keep going.
Exactly. So if one light bulb burns out in a parallel circuit, the others stay lit.
Okay, so that's why we use parallel circuits in our homes.
Yeah.
It wouldn't be very practical if one light bulb burning out caused the whole house to go dark.
Right, exactly. Parallel circuits are all about redundancy and reliability.
So they're more flexible and more dependable than series circuits.
That's right. And understanding these two basic circuit types lays the foundation for understanding more complex electrical systems.
It's all about building blocks, right? Starting with the basics and then working our way up.
Exactly. And that's what makes this stuff so fascinating. Once you understand the fundamentals, you can start to see how those principles apply to all sorts of amazing technologies.
Absolutely. And that's what we're going to be exploring in more detail in the next part of this deep dive.
Yeah, stay tuned because things are about to get even more electrifying.
I can't wait to see you in the next part. All right, resistors. I've seen them on circuit boards, those little colorful components. What exactly do they do?
Resistors do exactly what their name implies. They resist the flow of current.
So they're like the brakes in a car, controlling the electrical flow.
That's a good analogy. They control how much current is allowed to pass through a circuit.
And I remember the manual mentioned different types of resistors, like fixed resistors and variable resistors.
Right. Fixed resistors have a set resistance value that can't be changed, like setting a speed limit.
Okay.
Variable resistors, though, those let you adjust the resistance, like a volume knob controlling the flow.
So you can fine-tune the resistance with those.
Exactly. And then there's something else cool about resistors, those colorful bands you see on them.
Oh, yeah. Is there some kind of code? I always wondered about that.
It's like a secret language for electronics.
Yeah.
Those bands actually tell you the resistor's resistance value and its tolerance.
Wow. So much information packed into those little things.
Right. And the manual has a chart, figure 12.50, that helps you decode all those colors.
That's awesome. Okay, resistors control the flow. What about capacitors? What do they do?
Capacitors are like little energy storage tanks.
Oh, okay.
They store electrical energy in an electrostatic field. Think of it kind of like a battery, but instead of storing chemical energy, they store electrical energy.
Okay, so they're like tiny little batteries. And I've seen them in different shapes and sizes. Is there a reason for that?
Absolutely. Different types of capacitors are designed for different tasks. The manual mentions electrolytic capacitors, which are commonly used in DC circuits, and tantalum capacitors, which are known for their compact size and stability. Figures 12.110 to 12.120 actually show some pictures of those.
That's pretty cool. So the way a capacitor is designed really impacts how it performs. How do they act in different types of circuits, though?
Well, in a DC circuit, a capacitor acts like a gate. It lets current flow freely until it's fully charged. Then it blocks any further current flow.
Oh, interesting. So it's like it fills up and then shuts off the flow?
Yeah, that's a good way to put it. But in an AC circuit, it gets a bit more complicated.
How so?
Because with AC, the voltage and current are constantly changing direction, right? So
Hmm.
the capacitor's behavior actually depends on the frequency of that alternating current.
Okay, so the way it acts with AC depends on how quickly the current is changing direction.
Right. And this brings us to a concept called capacitive reactance.
Capacitive reactance.
Yeah. It's basically how much a capacitor resists the flow of AC current. And it's measured in ohms, just like resistance.
Okay.
And here's the interesting part. Capacitive reactance actually goes down as the frequency of the AC current goes up.
So at higher frequencies, the capacitor offers less resistance.
Exactly. It's almost like it becomes more permeable to those faster changing currents.
That's pretty cool.
Yeah.
Figure 12.121 actually shows a circuit diagram with a capacitor so we can see how this all works visually.
Yeah, it's good to see it laid out like that.
All right, we've talked about resistors, which control the flow, and capacitors, which store energy. What's the third key component?
Inductors. You could think of them as the magnetic cousins of capacitors.
Magnetic cousins.
Yeah. They also store energy, but instead of using an electrostatic field like a capacitor, they store it in a magnetic field.
Okay, and what does an inductor typically look like?
Most commonly, it's a coil of wire.
A coil. Why a coil?
That shape helps enhance its magnetic properties. Often you'll see those coils wrapped around a core material to make them even more effective.
Oh, that makes sense.
Yeah.
And just like capacitors have capacitive reactance, inductors have something called inductive reactance, right?
Exactly. Inductive reactance, we usually shorten it to XL, is basically the opposition an inductor offers to the flow of AC current.
Okay, so it's like how much it pushes back against that AC current.
Yep. And its value actually increases as the frequency of the AC current goes up.
Oh, interesting. So it's the opposite of capacitive reactance.
Exactly. Inductors become more resistant at higher frequencies. And if you look at figure 12.127 in the manual, you'll see the typical symbol used to represent an inductor in circuit diagrams.
Okay, I'll check that out. So we got these three players, resistors, capacitors, and inductors, each with their own way of interacting with current. How does it all come together in an AC circuit?
Well, as we've been talking about in AC circuits, that voltage and current are constantly switching directions, right?
Yeah.
So the interaction between those components becomes really dynamic. And this leads to a concept called impedance.
Impedance.
Yeah, it's basically the total opposition that a circuit offers to the flow of AC current. It takes into account not just the plain resistance, but also the reactances from those capacitors and inductors.
Oh, okay. So it's like a more complete picture of how much the circuit is resisting that AC current.
Exactly. Figure 12.134 in the manual shows a visual representation of this. They call it the impedance triangle. It helps illustrate how resistance, capacitive reactance, and inductive reactance all contribute to the overall impedance.
That's really helpful for understanding the bigger picture. The manual also mentions something called resonance, though. What is that all about?
Resonance is pretty fascinating. It happens when the inductive reactance and the capacitive reactance in a circuit perfectly cancel each other out.
So they balance each other perfectly.
Right, and at that point, the circuit's impedance hits its minimum value.
Oh, wow. So the circuit becomes very conductive at that specific frequency.
Exactly. It's like it's perfectly tuned to that frequency. And engineers use this principle of resonance in all sorts of applications, like radio tuners, filters, anything where you need to select a specific frequency. Figures 12.138 and 12.139 actually show some examples of resonant circuits.
Pretty cool. So resonance is about finding that sweet spot where the reactances cancel out. Now let's switch gears and talk about power in AC circuits. I have a feeling it's not as straightforward as it is in DC circuits.
You're right. It gets a bit more nuanced with AC. We have to consider two types of power: real power and reactive power.
Okay, break that down for me. What's the difference?
Real power is the power that's actually used by the circuit to do work, like lighting a bulb, running a motor, the stuff we want it to do. Reactive power is associated with the energy that's being stored and released by those capacitors and inductors.
So real power does the actual work, and reactive power is kind of like energy that's just sloshing back and forth.
That's a good analogy. And when you combine those two, you get what's called apparent power. We measure that in volt amperes, or VA. Figure 12.141 in the manual has a good illustration of this.
So apparent power is the total power capacity, but not all of it is actually doing useful work.
Right. And to understand how much of that power is actually being used effectively, we look at the power factor.
Power factor, what's that?
It's the ratio of real power to apparent power. A higher power factor means the circuit is using its power more efficiently.
Oh, okay. So if all the power is being used for actual work, the power factor would be 1.
Exactly. And the lower the power factor, the more power is being wasted, essentially bouncing back and forth between those capacitors and inductors.
Got it. So high power factor, good. Low power factor, not so good.
Right. And the manual actually gives a real-world example. They talk about a 220-volt AC motor that's pulling 5 amps from the line, but a watt meter shows that it's only actually consuming 930 watts.
So the power factor helps us understand the difference between how much power it's drawing and how much it's actually using.
Exactly. It gives us insight into the efficiency of the system.
Okay, this is all starting to make a lot more sense.
Yeah.
But how do we actually go about measuring these different electrical quantities? What are the tools we use?
Our trusty manual has us covered. It focuses on some essential tools of the trade: ammeters, voltmeters, and ohmmeters. They're like the electrician's eyes and ears.
Oh, right. I
Yeah.
remember learning about those. So ammeters measure current, voltmeters measure voltage, and ohmmeters measure resistance.
You got it. Figure 12.149 actually shows a basic ammeter. They're typically connected in series with the component you're trying to measure.
Okay, and voltmeters are connected in parallel to measure the voltage across a component, right?
Exactly. Figure 12.151 shows a simplified ohmmeter circuit for measuring resistance.
Cool. Anything else we need to know about using those?
One important concept with ohmmeters is zero adjustment. You basically calibrate the meter so that it reads 0 ohms when its leads are shorted together.
So it's like setting the baseline for accurate measurements.
Exactly. But to really dive deep and see those electrical signals in action, we need a more sophisticated tool. And that's where the oscilloscope comes in.
The oscilloscope. I always imagine those as being super high-tech. What exactly do they do?
The oscilloscope is like a window into the world of electrical waveforms. It lets us see the shape, the frequency, all those characteristics of those electrical signals that we've been talking about.
It's like we're looking at the electrical heartbeat of a circuit.
I like that analogy.
Yeah.
And the way it works is pretty fascinating. It uses a focused beam of electrons that hits a fluorescent screen, creating a visible trace. By applying voltages to what are called deflection plates, we can control the position of that beam. Figure 12.165 in the manual does a great job of illustrating that.
So we're using electrical fields to steer a beam of electrons and create a visual representation of the signal. And that allows us to measure things like amplitude, frequency, and phase, right?
Exactly. We can zoom in on specific parts of the signal, slow it down, and really analyze its characteristics. Figure 12.167 shows an example of a sine wave voltage being displayed on an oscilloscope.
That's incredible. It's like having a super-powered magnifying glass for the electrical world. So now that we have these tools to visualize and measure those electrical signals, let's talk about troubleshooting. Our manual focuses on 2 common problems in circuits: opens and shorts.
Opens and shorts, those are the classic troublemakers in electrical circuits.
All right, let's start with opens. What exactly is an open circuit?
An open circuit is basically a break in the electrical pathway. Think of it like a cut wire or a component that's completely failed. That break stops the current from flowing. Figure 12.170 shows how you can use a voltmeter to track down an open in a series circuit.
So if the voltmeter reads 0 volts, across a component that should have voltage across it, that's a sign of an open circuit.
Exactly. And you can also use an ohmmeter to confirm. It would show infinite resistance across that open component.
Okay, so opens are like broken connections. What about shorts? How are they different?
A short circuit, or just a short, for short, is like an accidental shortcut in the circuit. It happens when there's an unintended path of very low resistance. Think of it like a wire accidentally touching another conductor, creating a bypass for the current.
Oh, so instead of following the intended path, the current takes this shortcut.
Exactly. And that can be a problem because it allows too much current to flow.
Right, because there's less resistance holding it back.
Yep. And too much current can lead to all sorts of trouble, overheating, damaged components, even fire in some cases.
Yikes. That sounds serious. How do we detect those sneaky shorts?
An ohmmeter is your go-to tool here. If it shows very low resistance, close to zero, across a component that should have a measurable resistance, that's a pretty good sign you've got a short circuit. Figure 12.171 shows how to test for a short with an ohmmeter.
Okay. And I'm guessing the first step before we try to fix a short is to isolate that component from the rest of the circuit.
Absolutely. Safety first. Never mess around with electrical circuits when they're still live.
Good advice.
Yeah.
Now, the manual also talked about troubleshooting opens in parallel circuits. Remember, those are the circuits with multiple paths for the current.
Right, and troubleshooting opens in parallel circuits is a bit different because an open in one branch doesn't necessarily shut down the whole circuit.
Right, it's like having multiple lanes on a highway. A blockage in one lane doesn't stop all the traffic.
Exactly.
To troubleshoot this, you can measure the total resistance of the circuit and compare it to what it should be.
So if the total resistance is higher than it should be, that means you've got an open in one of those parallel branches.
You got it. And you can use a voltmeter to pinpoint which branch has the open by measuring the voltage across each one. Figure 12.175 shows how to do that.
Okay, that makes sense. So we've covered opens and shorts in both series and parallel circuits. That's pretty empowering. We're like electrical detectives now. But let's shift gears and talk about a different kind of power source. Batteries. Those portable wonders that power so many of our devices.
Batteries are amazing. They're like self-contained chemical factories generating electricity through chemical reactions.
Batteries, they're like these little magic boxes that provide portable power. But I have to admit, I don't really understand how they work.
Yeah, they're pretty amazing when you think about it, storing energy chemically and then releasing it as electricity. Our manual dives into the two main types of batteries, primary cells and secondary cells.
Right, so primary cells are those single-use batteries, and secondary cells are the rechargeable ones. It's like the difference between the AA batteries in my remote and the one on my phone. What makes them so different? Is it just a technology thing?
It really comes down to the fundamental chemistry inside them. Primary cells are designed for one-time use because their chemical reactions are essentially irreversible. Once the active materials are depleted, they're done. No more juice.
So they're kind of like tiny controlled chemical reactions that produce electricity. Then with secondary cells, the rechargeable ones, we can actually reverse those reactions.
Exactly. That's what makes them rechargeable. We can apply an external electrical current to force those chemical reactions to run in reverse, essentially restoring the battery's ability to store energy.
That's pretty cool. So when I plug in my phone to charge, I'm reversing the chemical reactions that happen when I use it.
Yeah.
But it's not like a magic reset button, right? Even rechargeable batteries eventually wear out.
You're right. Even though we can recharge them, those chemical processes don't stay perfectly reversible forever. Over time, the battery's capacity to store energy will decrease, and it'll eventually need to be replaced.
It makes sense. Nothing lasts forever. So what are some of the common types of secondary cell chemistries we encounter in our everyday devices?
Well, our manual talks about a couple of them. Lead-acid batteries, which are still widely used in vehicles, and nickel-cadmium batteries, which used to be popular for portable devices but are less common now. Of course, we can't forget about lithium-ion batteries, which are pretty much the stars of the show these days.
Yeah, lithium-ion batteries seem to be everywhere now. Phones, laptops, even electric cars. What makes them so great?
They have a really high energy density, meaning they can pack a lot of energy into a relatively small and lightweight package. They also tend to have a longer lifespan compared to some other battery types.
Okay, that makes sense. Speaking of those lead-acid batteries, the ones we usually find in cars, can you paint us a picture of what's going on inside those big, heavy batteries?
Imagine this. You have a bunch of lead plates submerged in a solution of sulfuric acid.
Sounds a bit dangerous.
It can be, but that's the chemistry that makes it work. So when you turn the key to start your car, a chemical reaction kicks off between the lead and the sulfuric acid. This reaction produces lead sulfate and water, releasing electrons that flow through the circuit and power your starter motor.
So it's like a controlled chemical reaction that creates the electrical current needed to get the engine going.
Exactly. And when we recharge the battery, we apply an external current that reverses that reaction, converting the lead sulfate back into lead and sulfuric acid. This essentially restores the battery to its charged state, ready to go again.
Pretty amazing. The manual goes into the nitty-gritty chemical equations for those reactions, which is pretty cool if you're a chemistry buff. But practically speaking, how do we measure a battery's capacity? How much energy it can actually store?
That's where the term ampere hour, or Ah, comes in. It's like a measure of the battery's fuel tank size. For example, a 100-all battery could theoretically supply 10 amps of current for 10 hours.
So the higher the hour rating, the more energy it can store.
Exactly. But it's important to remember that real-world conditions can impact a battery's performance. Things like temperature and how quickly you're discharging the battery can all affect how much usable energy you get out of it.
Okay, so it's not always as straightforward as just looking at the hour rating. And what about battery lifespan? How many times can you recharge a battery before it eventually wears out?
Well, there isn't a hard and fast number, but a helpful way to think about it is to compare a battery to a muscle. You can exercise it and recharge it, but over time and with repeated use, it's going to lose some of its strength. The same applies to batteries. Things like fast charging, deep discharges, and even extreme temperatures can all shorten a battery's lifespan.
So it's about using batteries wisely and taking care of them to get the most out of them.
Absolutely, treat them right, and they'll last longer. Now, we've talked a lot about batteries, which are great for portable power, but what about the systems that provide the electricity that powers our homes and cities? Those massive power plants and electrical grids, that's where generators come into play, right?
Exactly. Generators are the real heavy lifters, converting mechanical energy into electrical energy on a large scale, using those principles of electromagnetism we talked about earlier.
Exactly. They're essentially harnessing the power of motion and magnetism to generate electricity. And the most common type we see is the AC generator, often called an alternator, which produces that alternating current that powers our homes and businesses.
I remember figure 12.103 showed the difference between DC and AC voltage waveforms. That smooth sinusoidal shape of AC is what comes out of our wall outlets. But the power straight from a generator often needs a little refining, right?
Yep, that's where voltage regulators come in. They play a crucial role in ensuring a clean, stable, and reliable electrical supply.
So they're like the quality control managers of the power grid.
Exactly. They help smooth out any fluctuations in the voltage so that the power delivered to our homes and devices is consistent and safe.
And I remember learning that aircraft have even more sophisticated systems, like those generator control units or GCUs. What do those do?
GCUs are like the brains of the electrical system in an aircraft. They monitor and manage the generators, protecting the system from overloads and other faults that could cause problems. They're essential for maintaining the safety and reliability of the aircraft's electrical system.
It's amazing how much complexity goes into something we often take for granted, like plugging in a lamp. But what happens when we need to switch between DC and AC? That's where inverters come in, right?
You got it. Inverters are like the electrical translators, able to convert DC to AC or AC to DC depending on what's needed.
So an inverter makes it possible for an aircraft, for example, to use its DC batteries and generators to create AC power for some of its systems. Pretty clever. But now let's talk about taking that electrical energy and turning it back into motion. It's time to talk about motors.
Motors are the workhorses of the mechanical world. They take that electrical energy and convert it into the mechanical energy that makes things move.
From tiny motors in our smartphones to giant motors in industrial machinery, they're everywhere. Our manual dives into DC motors specifically, which are the type that run on direct current, like what you get from a battery. But the basic principle of a motor, whether it's AC or DC, is about using magnetic fields and electrical currents to generate rotational force, or torque.
Right. It all comes back to that interplay of electricity and magnetism.
So what's actually happening inside a DC motor to make it spin?
Picture this. You have a rotating part called the armature, surrounded by stationary field coils. There's also a component called a commutator, which acts like a tiny switch that changes the direction of current flow in those armature windings.
Okay, so we're switching the current direction in the armature. Why do we do that?
It's all about creating a continuous rotation. By switching the current direction, we create interacting magnetic fields between the armature and those field coils. That interaction produces a torque that causes the armature to spin.
So it's a carefully choreographed dance of electromagnetism that results in motion.
Pretty cool. And there are different types of DC motors, right? I remember seeing something about series motors, shunt motors, and compound motors. Why so many options?
Different types of motors are better suited for different tasks. Series motors are great for producing a lot of torque at low speeds, making them ideal for things like power tools and starter motors. Shunt motors are good at maintaining a consistent speed even under changing loads, and compound motors offer a combination of both characteristics.
Figure 12.306 actually shows how the speed of those different mototypes changes with different loads, which helps visualize those differences. So it's all about choosing the right tool for the job, depending on the specific application. What about AC motors, though? Those are the ones that power most of our appliances and big industrial machines. How do they work?
The fundamental principles are similar to DC motors. It's still about using magnetic fields and electric currents to generate rotational force. But AC motors are designed to work with alternating current, where the current is constantly reversing direction. Right, so how do those rotors spin smoothly if the current is always flip-flopping?
That's where clever design and engineering come in. The most common type of AC motor is the induction motor, where a rotating magnetic field in the stator induces a current in the rotor, causing it to spin.
Oh, so the rotor is always trying to catch up with that rotating magnetic field, but never quite gets there. That's why it's called an induction motor, right?
Exactly. And there are different variations of induction motors, like split-phase motors and capacitor start motors, which are designed with various mechanisms to ensure they start spinning reliably. Then there's another type of AC motor called a synchronous motor.
Synchronous motors, what are those used for?
Synchronous motors run at a speed that's synchronized with the frequency of the AC power supply. They're commonly used in applications where precise speed control is critical, like in clocks and timers.
So whether it's AC or DC, motors rely on this amazing interplay of electricity and magnetism to produce the motion that drives so much of our world. But I know that motors aren't perfectly efficient. Our manual mentions things like copper losses and iron losses. What are those and why do they matter?
Those are some of the unavoidable energy losses that occur in motors, and they reduce the overall efficiency of the motor. Copper losses happen because of the resistance in the windings of the motor, and iron losses occur due to magnetic effects in the core of the motor.
So we're losing some of that electrical energy as heat due to these factors.
Exactly. That's why engineers put a lot of effort into minimizing these losses to create more efficient motors that use less energy to produce the same amount of mechanical power.
Makes sense. Speaking of efficiency, I remember we talked about transformers earlier, those devices that let us change the voltage of AC power. Why are they so important, especially for something like our electrical grid?
Transformers are crucial for efficient power distribution. Imagine trying to transmit electricity over long distances using the low voltages we use in our homes. The energy losses due to the resistance in the wires would be enormous. It just wouldn't be practical.
So we need to step up the voltage to very high levels to transmit power efficiently over those long distances.
Exactly. Transformers allow us to do just that. We can step up the voltage to very high levels for transmission and then step it back down to safer, more usable levels when it gets closer to our homes and businesses.
They're like the electrical gearboxes of the power grid, allowing us to adjust the voltage as needed. How do transformers actually achieve this voltage conversion?
It all comes down to that principle of mutual induction we talked about before. A changing current in one coil can induce a voltage in another coil that's nearby. Figure 12.244 shows this concept really well. By changing the number of turns in those coils, we can control whether a transformer steps the voltage up or down.
It's all about manipulating those magnetic fields to our advantage. Now, the manual also mentions something called three-phase systems. What are those, and why are they important, especially for industrial applications?
Three-phase systems are a more efficient way to deliver AC power, especially for large motors. Instead of using a single AC waveform, they use three separate AC voltages that are out of phase with each other. Figure 12.330 shows what those waveforms look like. It's like three synchronized waves of power working together.
So instead of one big pulse of power, we have three smaller pulses that overlap, creating a smoother and more consistent flow of power.
You got it. This smoother power delivery is particularly beneficial for large motors, reducing vibrations and increasing efficiency. That's why you'll often find three-phase systems used in industrial settings where those big motors are common.
It's amazing to think about all this complexity that goes into something we take for granted, like just plugging in a lamp.
It really is. The world of electricity and electronics is a fascinating blend of fundamental principles and incredible human ingenuity.
And this deep dive has really opened my eyes to how much amazing science and engineering are packed into the electrical systems that power our lives. We've covered everything from the tiniest particles of matter to the massive systems that make up our electrical grid.
It's been a great exploration, and I hope our listeners have gained a new appreciation for the incredible world of electricity and electronics.
Absolutely. It's all about understanding those fundamental principles, which allows us to not just use this technology, but to really appreciate the brilliance behind it.
Exactly. And who knows what amazing innovations await us in the future as we continue to explore and harness the power of electricity.
It's an exciting time to be alive. So to our listeners, stay curious, keep exploring, and never stop learning. Until next time, stay charged up.